This question says a solution is prepared at 25 degrees C that is initially 0.13 molar ammonia, a weak base, with a Kb of 1.8 times 10 to the minus 5, and 0.44 molar ammonium bromide, and it wants us to it wants us to calculate the pH of this solution. So that's basically our goal here. So essentially what we have is we have NH3 aqueous, which is a weak base, plus water, liquid, and this is going to deprotonate water to form NH4 plus aqueous plus OH minus. And in this way, ammonia acts as a weak base. So this is a reaction that's what describes what's going on. In several of these questions, in this topic, you're given an acid, and it's a little bit more straightforward if you're given an acid. But I wanted to go over an example where you're given a base, because again, it's a little bit less straightforward. In order to calculate the pH of a buffer, one of the more efficient ways to do that is to use the Henderson-Hasselbalch equation, which is pH equals pKa plus log A minus over HA. And if you had an acid with a Ka, you just find the pKa, put the concentration of A minus, put the concentration of HA, and you'd be good to go. But with a base, again, it's a little bit more complicated. So we can rewrite this for a base. pH equals pKa plus log concentration B over concentration BH plus, like so. So now we have this expression written for a base. The problem is we don't know the pKa of this base. We know the concentration of B, that's 0.13 molar. We know the concentration of BH plus, because NH4Br is a source of NH4 plus, that's 0.44 molar. We could just plug those in. But what we don't know is the pKa, so we can't just plug that in. So how are we going to find that? Well, if you recall, the Ka times the Kb equals Kw. Said another way, Ka equals Kw divided by Kb. So Ka equals the Kw, 1 times 10 to the minus 14, and like in other videos, I'm ignoring the sig figs of this one. And then the Kb, it's 1.8 times 10 to the minus 5. The Ka equals 5.556 times 10 to the minus 10, where that's the sig fig. But we don't want to plug the Ka into our Henderson-Hasselbalch equation for the base. What we basically want to do is plug in the pKa. Well, the pKa is the negative log of the Ka. So we want to take the negative log of this. And when you do that, you find that the pKa equals 9.2553. And just so you know what I just did, I just took the negative log of the Ka in the calculator to find the pKa. So that's the formula that I did. And here, this is the significant figures. So now we know the pKa. So pH equals the pKa, 9.2553, plus log concentration of B is 0.13 molar, and over the concentration of NH4 plus, which is 0.44 molar. So I divide these two numbers in the calculator, take the log, and what I find is that pH equals 9.2553 plus negative 0.52951, where that's your sig fig. So I have a positive plus a negative, so I'm essentially subtracting. And when I do that, make sure I don't go off the screen, I want to know that pH equals 8.73. So this is a fairly complicated process with many steps, but it can be done for a base. Again, if you have an acid and you're given the Ka, you can simply find the pKa by taking the negative log of the Ka, use your concentration of A minus, which will be over here, and your concentration of HA, which will be over here. Note that these are bases, so that's where they would be, but those are actually bases and not acids. So that's basically how it works.